is going up every day. When it comes to AI, I've taken out a lot of slides because I wanted us to get to the hands-on examples very quickly. But when it comes to AI, we have to think of the different stages of designing a system with AI. Okay. So here, for example, I've put all of these stages in one shot, but typically the way we start out is with the data preparation stage. Okay. And in data preparation, this means data pre-processing, feature engineering. So for example, if I'm trying to um, take my phone data, for example, and I want to measure my the number of steps I'm walking. Okay, I want to build out an AI algorithm that tells me how many steps I've taken, whether I'm walking, running, whether I'm sitting, standing. Basically, a human activity classification. In that case, I know that when the data comes in, there's going to be a lot of noise on top of the signals, right? Ideally, when I'm walking, right, I should find the signal with certain spikes corresponding to when I'm stepping. But uh, unfortunately, or fortunately, in some cases, I don't see a clean spike. I'm going to see noise everywhere. And depending on where I am, if I'm running on smooth ground, if I'm running on the beach, or if I'm running on uneven ground, my signal will change, right? So in those cases, I want to pre-process my data, take out some of the noise so I can focus only on that clean signal. In some cases, the raw data I have might be so much that what I need to do is take out some representation of that signal. That's where feature engineering comes in. Feature engineering is really asking, do I need all this data, or can I pick out certain points like the mean of the signal or the standard deviation, or what is the peak value, what is the time between peaks, right? All of these become feature engineering cases. And in some cases, like let's take predictive maintenance, for example, right? I have a car and I want to know when my car is going to fail. Um, I want that AI model that predicts failure. I cannot sit and wait for my car to fail 1000 times in order to collect this data and then build my AI model, right? What I want to do instead is to simulate some data. And the car is a physical system. We know the different components. So if we get those components to work together in a simulation, we can inject faults. We can say, okay, engine issue, uh, oil flow issue, brake pads are not working or something like that. And we can generate what that failure data looks like. Okay? So that's my data preparation stage. After I've prepared my data, the next thing I want to do is build out my AI model and train it on that data. So this would mean, designing and fine tuning a model. There are thousands of models out there. How do I pick the right one? And what Kunal showed you yesterday could be one way. With the experiment manager, not only can you change hyperparameters, if I want to try out 100 different model architectures, I can also do that with the experiment manager. Right? Um, if I have a model sitting in Python or PyTorch or TensorFlow, whichever we are using, I can bring that in to MATLAB and then work with that. And also, I want to be able to understand how that model is performing on some validation data. So Nikhil would have shown you that with the classification learner app. So these two stages, these take care of, okay, the AI modeling, data preparation. And now we come to simulation and test. After I've built that AI model, if I'm using it in a real world application like biomedical, predictive maintenance, health monitoring, this AI model is not the only algorithm. It's going to sit in a system that has multiple other parts. And that's where integration with complex system comes into picture. Sometimes, most times, we want these AI models to work in real time. They have to work fast. So not only should they give us correct predictions, but they should also give us timely predictions. And can it do that while it's sitting in a larger system, basically? Right. And finally, the last stage of it is I've designed everything. It's working fine. It's working with my larger model, but To actually put it to use in the real world, it has to be deployed, and it can be deployed on, the cloud, on a server, but it can also be deployed on a piece of hardware. So something like a Raspberry Pi, an NVIDIA Jetson, uh, a small chip, ECU chip that sits on a car, right? And so this deployment stage requires a lot of engineering because there is always a memory constraint. I only have, let's say, 100 MB to deploy an AI model, but I've gone through these first three stages and my final model is 500 MB. That is not going to help me practically, right? So can somebody take a guess for me as to which stage here takes the longest time? Is it data preparation, AI modeling, simulation test, or deployment? You can use the chat, you can use um, you can unmute and speak also. But what do you think is the most time consuming stage here? Okay. Ranjana has said simulation. Okay, interesting. Okay, we're getting a couple of answers now. I'll just wait a few more seconds. So pre-processing, simulation, any other guesses here? Data preparation, okay. Pre-process, okay. So I think, okay, Sonali has said deployment, right? Deployment is a good one, actually. Yeah. So I'll tell you what the answer is. But before that, here I've given you, stage one. After you're done with stage one, you go to stage two to three, three to four. That's not how it works in practice. In practice, what's going to happen is you can see this yellow, this orange circle here, right? In practice, what happens is you keep going between stages. So I'll do all of my data preparation. Let's say I spend one day on data preparation. I come to AI modeling, and then I realize my data is not prepared properly. So I have to go back, work on it again, then come back, right? And like Sonali was saying with deployment, let's say I've done everything and come to deployment. What if it doesn't fit, right? Then I have to go and change my AI model. I'll have to do some compression. After that, I need to test it with a larger system. So there is so much back and forth between these stages. And the answer to which stage individually takes the most time, usually it's data preparation, because you probably heard of this saying, right? Garbage in, garbage out. If I don't prepare my data properly, there is no use spending time on the AI modeling bit because the data itself is flawed. So yeah, correct answer is data preparation or pre-processing is the most time consuming stage. Okay, so that is in general the AI workflow. When it comes to signals, what is it? How do we go from this thing to signals? It's fairly straightforward. We start out with our signal here. Okay. Then we take our signal and we extract some features from it, feature engineering. After that, we do the AI modeling. So this represents a neural network. We validate the performance on its own, part of a larger system. If I have to compress my model, again, I need to retrain and validate it. And the last stage, of course, is deployment onto some kind of embedded device. So this is basically what happens in a AI signal processing application. Okay. For today's example, what I'm going to show you is actually AI for an advanced signal processing application. And here what we're looking at is actually a heart signal. It's from an electrocardiogram signal, so ECG, if you've heard of that. If you've ever had to do a full body medical test, heart rate is something that they check, and what they're checking is ECGs with those electrodes that they are connecting. Okay. So when it comes to electrodes, the ECG electrodes and what signals they are capturing, this is basically what it is. Okay. In the top plot, you can see something that says NSR. NSR is normal sinus rhythm or normal sinusoidal rhythm. It's basically a normal heartbeat. Okay, so here we have the spike. There's a PQRS structure to this, and a normal heartbeat looks like something like this, where you'll have a small dip, a spike, a smaller increase in value, a bump, and then this keeps repeating. And what you'll I'm going to ask you a question then. What is the difference between NSR, which is normal, and ARR, which is an arrhythmia? So the abnormal rhythm condition. Have a look at these two graphs, and in the chat, let me know what do you think is the difference between these two graphs, blue and orange. Take a very careful look and see what you think is the difference between these two. Orange, okay, inverted P wave, okay. Orange graph, the second peak is not normal. Okay. Anything else you're noticing? So what you're actually noticing is the amplitude variation. Is there anything in the time that you're noticing? The clue is in the name of the signal. So the top one is normal and the second one is arrhythmia, abnormal rhythm. So what is the other difference you can see here? A hint is look at the spacing between the peaks here, and then look at the spacing between the peaks here. Yeah. Signal is shifted. The peaks are shifted, right? So this is a heart that is not beating at a fixed rhythm, basically. Yeah. Peak value not being similar is fine. It's more about the rhythm and the structure of the wave that we're, yeah, exactly. So here, this person who we've taken the second signal from, their heart is not beating regular intervals, which is very dangerous. Because if your heart doesn't beat regularly, it means that pumping is not happening regularly, and delays in pumping can lead to major issues, right? With cells not receiving enough blood. So this is basically the difference between these two types of signals. And what we're trying to do is we've got some ECG data, raw data. We've just got these raw waves. We are going to come up with an AI model that can classify between normal and abnormal reading. Okay. Okay. So the way we're going to do that is basically two approaches. One is a machine learning approach. The other is a deep learning approach. In the machine learning approach, we are doing feature extraction and then applying machine learning algorithms. In the deep learning approach, we are taking the entire signal, but we're actually computing a time frequency representation. How many people here have heard of scalograms? Or have you heard of spectrograms? Can we get in the chat spectrogram or scaleogram? Yeah. If you've heard of one of these or you've heard of both, just mention which one you've heard about. Spectrogram. Okay. Okay, no problem. We can discuss that a little bit. So the basic idea here, left-hand side for the machine learning case, we will extract features from the signal. And on the right-hand side, we're going to convert our signal into its time frequency representation. Okay, I'll explain what that means. So now I had this very simple example where we took these signals and we computed some features like what is the mean value, what is the distance between these peaks, what is the standard deviation, all of these basic statistics. But for today's example, I'd actually brought a slightly more advanced example. Okay, and that example is we're going to compute the features from these signals using something called wavelets. Okay. So for those of you who don't know what is a wavelet, uh, it's a wavelet processing is signal processing technique. It's very similar to the Fourier transform, FFT. Okay, so FFT, what we do is we assume that our signal, it is composed of sinusoids of different frequencies, right? And if you add up these different sinusoids, they will give you the final signal. That is my FFT, fast Fourier transform. And the way we compute it on a computer is called the FFT, fast Fourier transform. In wavelets, it's very simple. But what we're saying is, instead of a sinusoid that goes from infinity to minus to plus infinity, a wavelet has a start and a stop. Okay. So this is what a typical wavelet will look like. And we're assuming that our signal is made up of different wavelengths with different properties. Okay. So here, for example, on the right hand side, we have the sine wave in red and we have a wavelet in blue. There are different types of wavelets. This is a SIM4 type of wavelet. Okay. So how does this work? There's a nice visual that will show us. This is my original signal in red. And now what I'm going to do is I'm going to take different wavelets of different shapes and I'm going to slide them across my original signal and I'm going to compute what are the coefficients. Okay. If you're finding this a little difficult, that's okay. Just bear with me for a few slides. But those of you who are interested in these details, I'm explaining it for you. In a few slides, I'll show you the hands-on of how do we actually compute these things. Okay. So that's my first wavelet. Now I have the second wavelet, and now I have the third wavelet. What was the difference between those three wavelets? I'll play it again, and you can let me know your observation. But just watch closely and tell me what is the difference between the three wavelets that we're sliding across our signal. Anyone? What are the difference between our wavelets? Just observe closely. I'll show it to you last time. Okay, somebody frequency is different. Okay, exactly. So one wavelet is stretched, one wavelet is normal, and one wavelet is compressed. And why we're doing that is because it captures different frequency components. That's all. Okay. So the way this is called the continuous wavelet transform. And depending on how much you stretch the wavelet, you'll be capturing different data. So if you have a stretched wavelet, a low frequency wavelet, you are capturing the slowly changing parts of the signal. If you have a compressed wavelength where the frequency is very high, you are capturing the high frequency component of your signal. That's basically it. Okay. So I'll leave these slides for you. You can have a look at them. What I'll do then is I will now show you how the wavelets are used to extract features. Okay, so basically we are doing wavelet scattering. It's a series of operations where we keep taking wavelets of the signal and then we get a feature set out of that signal. So instead of taking the signal and having 10,000 samples or 100,000 samples, we're now using wavelets to capture features in different frequency and scale. And instead of 10,000, we can reduce it maybe to 100 or to 200, 500, depending on your use case. Okay, so I take my signal. I will have some fixed signal length. I'll apply it to a wavelet scattering and then I will get some features. Those features, I will pass it to a classifier and it will help me classify whether in this case it's a normal or abnormal signal. Okay. So this is the exercise we're going to do. Like I said, if you want to follow along, feel free to do that. Otherwise, if you just want to watch and try it out later, you may also do that. Okay. Okay, so let me come into MATLAB. This is my MATLAB window. Let me make it slightly larger. Okay, is this visible for everyone? Is the size of font okay?
Yes, ma'am.
Yeah, okay, sure. So this is the folder you will have access to. And if you open it, you'll see all of these. There are some data files, um, some functions that are needed. I've put in some other exercises here. Remember, I told you there was a simple exercise on extracting features. So this is basically it, right? Here we have a signal. We're going to extract machine learning features, and then we'll perform the classification. So we can do this one as well. I think we have enough time.
Ma'am,
And
sorry to interrupt.
yeah,
Someone has said, can you zoom it as slightly?
zoom it some more. Okay, okay, sure. So this one is the maximum I can zoom. I've put it at 175%. Is this okay?
Yes, ma'am.
Yeah, okay. This is the best I can do. I'm sorry, but okay. So uh, I'm just showing you all of the examples you can try out. This one uses feature extraction and domain knowledge. So we have the signals and we're actually computing the difference between these peaks and so on. Okay. So all of these files that you need to compute the difference between the peaks are available here. Okay. Um, sure. So what I'll do is let me go through the example I had planned for us, which is wavelet scattering. And if time permits, then I'll show you the feature extraction one where we take the difference between peaks. And then last we'll end with the CNN or, converting the signal to an image and then working with that. Okay. So I hope you're all comfortable with the MATLAB environment. Here, this is my, let me show you what it will probably look like. Um, yeah, this is what your MATLAB will probably look like. There is this ribbon up here, which I will fold up. There is all of the files. There's a workspace here. So if I create a variable a is equal to 10, it will now turn up in my workspace. And if I do b is equal to a plus 5, b being a new variable, any variable I create, it will be in my workspace. Okay. So to clear my workspace, I'll type clear, and to clear my command window, I'll type CLC. Okay. And to run these exercises, obviously we can, write line by line here, but when you're working on something complicated, it's always better to use a MLX file. MLX is like a notebook. If you've used Jupyter notebooks, you'll have, uh, you can write your code and text everything in one document, right? It's a dynamic document. A live script is very similar to that. There are some added functionalities as well. Okay. So let me jump into our example today, the hands-on. And if you have questions at any point, just drop it in the chat or signal to me, and I'm happy to answer the questions for you. Okay, so I won't talk about all this detail because uh, we don't have that much time. But when you're going through these exercises on your own, please read through. This is really useful information. And basically, what we're doing here is we've got a normal signal and we've got an abnormal signal. Okay, and we're trying to distinguish between patients who have normal heart rhythm and abnormal heart rhythm. Okay, so one thing I would suggest to you, right, is when you get the folder, let's say you have access to the ECG folder, right click, um, right click on it, add to path, select folders and subfolders. So this will actually add all of the files that you need to your working directory. Okay, otherwise you'll have file issues. It will say things like I cannot find the file or something like that. So just add all the folders. The folders appear gray if they're not added, and they appear bright and yellow if they're added. So you might want to do that before you start. Okay, so first thing I'm going to do here is I'm going to run the section that starts off saying data preparation. And how do you run a section? You can, under live editor, you can go to run section, or the easy way to do it, which I like, is you just click on the left hand side bar here. So what I've done is I've basically loaded in this physionet data.mat. Okay. If I look at let me just try to sorry, just 1 second. Yeah, sorry about that. Okay, so like I was saying, the first thing I needed to do is to import the data that I have. And I'm just creating a variable called signals, a variable called labels, and the sampling frequency. The next thing I'm going to do is just to explore the data a little, maybe. So let me clear all the output so that we can see it running in real time. Okay. So here I have my, what I'm going to do is take the first 5 rows of the signals variable and the labels variable. So let me run that. And here you can see something very interesting. Some signals have 9,000 points and some signals have 18,000 points. This is not very uniform, and so obviously we need to fix the length and then work with those signals. Okay. Additionally, if we look at the labels, so remember this is label data. The first 3 signals here are normal and the next 2 are abnormal. Okay. So let's take a quick summary. We have 5,788 signals, 738 are abnormal, and 5,000 plus are normal signals. Okay. So that tells us basically what our data set looks like. And now let's look at a signal length histogram. So I'm using the histogram function here, and I'm computing the length of the signals. Okay. Now the issue is, remember that we need to have standardized length. So we need to come up with some logic to standardize the length for the signals. One basic logic is that we've used in this case is 9,000. Given that most of our signals are 9,000 samples in length, we are going to fix our working length as 9,000. Anything below 9,000 we will ignore for now because it's a small value. Anything above 9,000 we will try to split it up. Okay, so if it's 10,000, we will split it up into 9,000, and 1,000 we will discard. If it's 15,000, we'll split it up into 9,000 and discard 6,000. If it's 18,000, we will split it up into 2 signals of length 19,000. That's the basic logic there. Okay, and that logic is captured in this function called segment signals. Okay, so I'll run the section. And if you're interested to see what is in this, I will select segment signals, right click, and I can click on open segment signals. Okay. So this will open up the function And that shows me how I'm doing the segment signals. Is this clear? Okay. So now, if I plot the first 10 signals, you'll see that everything here is now 9,000. So I've taken care of the different lengths of the signals. Now, remember that this is all part of data pre-processing. So some of the data pre-processing is very boring stuff. It's just taking care of my signal length, seeing if anything's missing, discarding that, and so on. But another part of feature engineering data pre-processing is actually more involved and requires more domain knowledge. So this is what we look at using wavelet scattering to figure out what are the features here. Okay. So if you want to read up about this, there are a lot of links that you can follow. If you want just the basic outline, it's given here in this live script itself. But what we're going to do is use the wavelet scattering function. Okay. So here I'm saying this is the length of my signal. I'm using wavelet scattering, and let me run this and show you what we actually get. So if I go to my command window and type SF, you'll see that it is a wavelet scattering object. Okay, I've not performed the signal processing yet, but I've just created a wavelet scattering object. Okay, so here this object has different factors, and I won't get into detail of that. But if you're interested in wavelet scattering, what you can do is go to the help section. So you click on home, come to help, and it will take me to the online help. Okay, here let me type in wavelet scattering, and I can go and read up on this. Okay, so this is what wavelet scattering is. If you want to see what all of the objects properties mean, you can go and read that up. Okay, if you want to try out some examples, you can scroll to the example section here, and it will show you examples to perform wavelet scattering. Okay. So that's how you use like the documentation to help you understand some of these functions. Okay. Now okay. So now what we want to do is we want to, you probably know this idea, but when you have in machine learning or deep learning, you have a huge amount of data and you need to train the model on some data. But the thing is, we don't train it on all the data. We don't train it on 100% of the data. Some of the data we use for training, and the remaining data we're using for testing or validation, right? So in that case, I'm going to first split up my data set. Okay. I'm going to split it such that 75% is for training and 25% is kept away for the testing validation. Okay. And so when I look at, if I run this, and if I look at, let's say, length of IDX train, this will tell me how many samples I have for training. And if I look at IDX test, this tells me, oh, sorry. Okay, so IDX train will have ones and zeros, and IDX test will also have ones and zeros. Okay. If it's a 1, it means that sample was taken in the testing data set. If it's a 0, it means that sample was not taken in the testing data set. Okay. And so if I do a sum of all the index values in IDX test, it tells me 1,413 are for testing, and that's the wrong name, and 4,242 were taken for training. Okay, so that's a 75-25% split. Now this part is where we're actually doing the scattering, wavelet scattering, to take the features. Okay, and so this one will take a few seconds to run, but we're basically, what we're doing is we're taking the IDX train index values, all of the signals in those positions, and we're applying SF. Remember, SF is a scattering wavelet scattering object. Okay, so we are applying that to all of these signals that are in the training set. This will take a few seconds to run because wavelet scattering is not an easy operation. It's a pretty computationally intensive operation. So I'll just let this run for a few seconds, and if you have questions, please let me know in the chat. Okay, it looks like there are no questions so far. I hope that you're following along here. Okay, so I won't get into too much detail with this part, but we are basically reshaping some of the data that we have. So remember, SMAT is the scattering matrix. So if I look at size SMAT, okay, these are the sizes that I have. Okay, so that's a lot of data essentially. And what we've done, remember, is we've taken our signals and we've broken them up into features or series of features. Okay, so now that I've actually expanded my set, what I've done is, okay, if you notice what we had before, if I scroll up a bit, it is the signals data here, right? Let me look at size of signals. Okay. And let's take one of these signals and let's look at its size. Okay, so basically what I'm trying to say is, originally when we started with our raw data, we had 5,655 different observations, and each observation had 9,000 samples. Okay, so that is a lot of data for us. And imagine processing 9,000 size vectors. That can put a lot of load on my system. After I've done all of my feature engineering, I end up with 38,000 observations, but each observation is just 262 samples. So essentially what I've done is the size of the data I have to process, the length of each vector has gone from 9,000 to 262. Okay, but there is a compromise because we have more data to more observations to work with. Okay, so I'll come back to the bottom here and I'll put everything in a features table. So the features table will have all of these features that we've extracted, but we will also apply the labels. Okay, so those labels that we had from the original data, we are now splitting it to match our features, and we're just appending everything into one table called features table. If it was confusing till now, I understand, but let's say if you want, just assume that all of the machine learning features I have are in my S features table. And now we're going to do the AI part. Okay. So to do the AI modeling, obviously you can write code to do it, but I'm going to show you how to do it using the classification learner app. Okay. Let me go into the apps and let me go to the machine learning and deep learning. This is where I have the classification learner. So this is the app, it's opened up. You all have probably seen this day before yesterday, right? When Nikhil did his session.
Yes, ma'am.
Yeah, okay, okay. So let me go into bring in some data from my workspace, and I will bring in the S features table. Look at the dimension here. Okay, it's 38,000 cross 263. Okay. And if I look at my data here, you can see that there are 262 types of features. And by default, it's assuming that the response is the class variable. Okay. I can do things like, set aside validation, test data. Test data, we already kept aside 25%. So let that be. We'll just use training as well as validation here and start the session. Okay. So now this is what my data looks like. And I can go and try different combinations of the features. But unfortunately, we see that it's really difficult to distinguish between the features from these two classes, right? So in that case, I cannot just draw a straight line and based on these features and separate them out. I need to use AI models. Okay. So I don't know if Nikhil showed you this that day, but let's say for some reason you think 262 features is too much. What you can do is go to feature selection and you can manually choose which features you want, or you can use some kind of statistical methods. These are all statistical methods to help you select the features. Okay. What I will do then is go and pick an AI model. So is this something you all saw yesterday, the classification learner app and trying out different models?
Yes, some of them.
Okay. Okay, fine. So what I'm going to do now is instead of picking out individual models here, I'm going to pick out all of these models that are quick to train. Okay, I can even pick all and that will choose every model that is here, but I'm going to pick all quick to train. Okay, and then I will train the selected model. Is anyone trying this out on the site? Please let me know in the chat. If some of you are trying this out on your own, please let me know in the chat. It would be good to know. Anyone trying it out? Okay, so here you can see, oh yeah, yeah. So it's a slightly big file, but it has all the data that you need there. Um, okay, so here you can see this is taking a little time, but it's training 8 models in parallel. This would depend on the number of cores you have on your machine. Okay. So for me, it's training 8 models in parallel. And one of these is actually, okay, it looks like this decision tree, medium-sized decision tree, is giving me 91.5% accuracy, which is pretty good. Okay. So if I click on this, I can go and look at some of the features of this model, right? What are the hyperparameters of this model? Did I do any feature selection? In this case, I did not, so there are no feature selection there. It also tells me things like sorry, this is just taking a few seconds, but yeah, we can see that some of them are, uh, they're mostly doing well, but it looks like this tree seems to be the best performing model here. And this tree will have, it will tell me what is the accuracy, the cost, prediction speed, training time, and so on. Okay. And the thing is, why try so many models, right? When you're submitting a paper or you're submitting a report, one of the common questions is they ask you which models did you train? And when I've gone to conferences and seeing people say that we tried 3 or 4 models because uh, we read a paper and they tried these models, which is fine. But now when you're submitting, papers and conference presentations, they also ask, why did you limit yourself to these 3 models? So in those cases, it's better to try a larger set of AI models or machine learning models and then do a comparative study to explain exactly why you've picked a particular some one of these models. Okay. So here, for example, let's assume that this is the best performer overall, and let's inspect some of its results. Okay. So under the plot and results, I can look at multiple things. Let me look at the confusion matrix here. Okay. So the confusion matrix is, anyone here knows what a confusion matrix is? Can somebody try to interpret for me what I'm seeing on the screen here, all of these numbers? Anyone wants to take a try and see if they can interpret what this means?
Ma'am, it basically shows the performance evaluation.
Right, ma'am. That's right. Yeah. So on the x-axis, you can see it says predicted class. This is basically what the model is predicting. And the y-axis, it tells you what is the true class. Okay, which means what is the actual labels. And what we're doing is we're comparing what the model is saying versus what the truth actually is. And so here it tells me my model predicted normal 32,600 times when the class was actually normal. But my model predicted normal almost 2,000 times when the class was actually abnormal. So it made a wrong prediction. Similarly here, my model predicted abnormal when the signal was normal around 800 times. And it got it right. It said normal when the true class was, it said abnormal when the true class was abnormal around 2,700 times. Okay. So that's not a very great performance when it comes to the abnormal class. Okay. Because when it's truly abnormal, my model is getting it right only about 60% of the time and wrong about 40% of the time, which is not ideal. But when the case is normal, it's doing it 97.5% versus 2.5%. Okay. So different models will have a different breakup of their performance. Let me look at this one, for example, a logistic regression. If I go to the logistic regression model and I look at its confusion matrix, here we will see its breakup. It's even worse. On the normal side, it's performing very well, but on the abnormal side, it's performing even worse than my the decision tree model. Okay. So what do I do with this decision tree model? Okay. How can I use it further? One thing obviously is I can generate a results table, and this basically will compare all of the models that I have tried out and trained. Okay. So now this model, some of them are still training, that's fine, but you can see a lot of them have completed, and so we can compare their performance in terms of all of these metrics. What I can do is, let's say I'm interested in learning how to write code for one of these models, right? I can click on the generate function button here. And what this will do is it will write up all the code that's needed for me to get that classifier, right? In this case, it was the tree. So it's writing all of the data pre-preparation, or the, like, if I did any feature selection, it would write that code for me. In the AI modeling, it's written the code for me. It's written the training code, the validation code, and everything. And everything that I did in the app with clicking, it's doing it here. It's given me the code, so I can use it as it is. Okay, I won't save it, but I'll go back to my classification learner. Another thing I can do is export the model, obviously, right? So I can export the model to Workspace. So let me export that. And what you'll notice is that this little green thing has come up here in MATLAB. That's because I'm using a parallel pool to perform the AI modeling part. So remember, I was running 8 in parallel. That's using the parallel pool. Okay. So I can export my model and call it train model. So that will happen there. And now it's ready to use. Okay. So let me actually stop the training of these other models, because I just want to move a little faster here. But let me stop training them, and let me come back to my script here. Okay. So we've done the training, and now the next thing is that we probably want to validate it on some data. Okay. Validation of the data means we are now applying all of this feature engineering to our test data set. Everything we did, uh, wavelet scattering, reshaping the labels, putting it all into a test table. We're doing that for the test data. And we are going to take our trained model that we have. We're going to give its predictions for the test table. Okay. And I'll walk you through this code and tell you what it means. But let me show you what it's saying here. Okay. So when I trained and exported the model, it comes in as the train model, and I'm getting instructions that say, if you want to predict with this model, use the predict function. Okay. And if you want to read more about it, you can follow this link, and it will take you to a documentation page that explains how do you actually use this model. Now remember, the wavelet scattering takes a couple of seconds to run. So we'll put that to run, and we'll basically apply the model to this test data. Does anyone know what this function is doing? This NNZ function? Anyone wants to take a guess? Normalization? No, not really. I mean, good guess, but essentially what we're doing is, let's see, okay, we're making the predictions with YFIT. Okay, so we are comparing YFIT to S labels test. What that is doing is, we're saying, is the prediction equal to the label data, to the true data? Okay, and if it's equal, it means it's a 1. If it's not equal, it means 0. So when we do that, NNZ is to sum the non-zero values, basically. So it's a very smart way, it's a very quick way to compute the accuracy. This function on its own, if I run it, let me run it, it will say 11,635. And if we divide that by the total number of test labels, which is 12,717, we are getting the accuracy. So the accuracy is 0.91. Okay. And last but not least, we'll try a confusion chart. And the confusion chart here will give us the predictions, the true versus the predicted class. Now I know the accuracy is not so great for the abnormal case. Can somebody tell me why the accuracy here is not good? And this, remember, or to let you know, this is related to the data that we're training the model on. Any guesses as to why it's doing really well for normal, but it's doing poorly for the abnormal class? Shape is fine because that is something that we should be able to capture with our AI model. The real reason this is happening is because we have an unbalanced data set. For the normal case, we have 5,000 data points. For the abnormal case, we have only 700 data points. Okay. So ideally, what we should do is we should either get more abnormal data, or we ignore most of our normal data and make sure both of them have an um, equal number of observations. So when you're trying this out on your own at home, I would suggest, instead of using all of this data, this normal data, reduce the number of normal samples. It's very basic coding you'll have to do in three lines of code. You can actually achieve this. Okay, so I want you to try it out. And with that, I will take a quick break here before moving on to the deep learning part. If you have any questions, do drop them in the chat. I'll be back in a few minutes. Okay, yeah. Hi, I'm back. So I think there is one question in the chat around how many images we have. I'm not sure I understood that question because here we were not actually working with images. We were working with signals directly. So the images example we're going to do now, the biomedical imaging. So let me start the next one. And if you still have a question, Sachin, just let me know. Okay. Yeah, thanks. Okay. So When it comes to deep learning for signals, there are some architectures like LSTMs or that can RNNs and LSTMs that we can use. But what we're going to do in this case is we're going to look at a CNN based application. So if you're interested in seeing some of this, you can, just Google it and say MATLAB, RNN, or LSTM. You'll find examples around it. I think even in the uh, resources I've shared with you, the exercise files, there'll be some exercise on LSTM as well. On the other hand, what we're going to look at is to take a signal and convert it to spectrograms, or in this case, scaleogram, and then treat that as an image. And the rest of it, you're probably familiar with CNNs, but pass that image through the network. I'll just go back a little to show you this part where this is what my signal looks like, the ECG signal. And then if I compute the scaleogram from it, this is what my scaleogram would look like. Okay, so here you can see the spikes, you can see the energy distributions, and scalograms are computed from the wavelet transform. So some of you from the signal processing background have seen spectrograms, which are computed using Fourier transform. Scalograms are computed using the wavelet transform. Okay. Yeah, so how do we do this? What is the process here? Is I have some signals, I compute their scalograms, I design a neural network that I will train the neural network on this data, on this scalogram data. Okay. Then that's the training part. Now, how do I actually use it is I take a new signal, I compute its scalogram, and I pass it to that trained network. So that network which I had trained, I now bring it here, pass in new data, and it will do the classification for me. Okay. So if you're not familiar with convolution neural networks, basically these are neural networks that are extracting features from the signal using convolution. So in wavelets, remember we took our wavelet and we slid it across our signal. In convolution neural networks, what we're doing is we have, instead of wavelets, we have convolution filters. And those convolution filters, we're now sliding it across our images. And that output is then passed through multiple layers. So here you can see in convolution, I have a convolution layer, then some post processing. Then I have another convolution layer, post processing. So you can stack up all of this convolution and eventually pass it to some um, layers that just do multiplication and addition, apply some nonlinearity, and then that's basically how my CNN works. Okay. So if you know CNNs, you're probably familiar with all of this. If not, you can take a look at some of these slides. Okay. So this is the second example, right? If you want to check out the LSTM example, you can follow it here, right? I'll show you what that looks like, and I'll put these slides in the same drive link that I shared with you, so you have access to this. Okay. I don't know where my cursor has gone, but this is basically what it is. And you can follow this example and try out the LSTM use case. Okay. So sorry, this, okay, yeah. Okay, so let me go into MATLAB now. And let me first start by clearing everything. Okay, and I'll go to the deep, yeah, I will share the PPT, Rohini. Here I'm going to go to exercise 2, ECG, DLL, CNN. Okay. So hopefully this one tends to be a little more intuitive. So what I'm going to do is start by again loading the data. So Sachin, to answer your question, in the database, not database base, but there's a data set called physionetdata.mat. This has all of the signals, not images. Okay. So again, we saw this last time where we brought the signals, we plotted their lengths. Here, what we're going to do is we're just going to plot two of these signals to see what they look like. Okay. And again, we're doing that exercise of segmenting it into each signal having 9,000 samples, basically. Okay. In this case, we're calling it feature generation, but basically what we're doing is we're getting images. Okay. So we have signals. Remember, we have a signal. And we want to compute an image or the scaleogram, and that will be used for the model training. Okay. How do we do that? There's something called a CWT, which is the continuous wavelet transform. And we're going to apply the CWT to our signal here. Sorry, I know I'm I'm changing the font size, but just to show you all the code at once, we're basically doing this, right? So here, if I compute the continuous wavelet transform, this is what my scaleogram looks like from my original signal. I'm using this function. Okay. Now there are many different properties we can use to generate the scaleogram. So if I want to hard code these properties, I can create a filter bank and then I can apply that. It's just a way to ensure that I'm applying the properties that I'm really interested in. For example, how many wavelets, what are the frequency bands, what is the times, the window we want to slide across. All of that can be captured in my CWT filter bank function here. Okay. And now we need to do this on a huge amount of data, right? So I won't run this live because this takes a lot of time, but if you're interested to see how to do something like this, there is a function prepare CWT images.mlx that can help with that. Okay, so Sachin is asking, can you please let us know how to read scaleogram? Okay, I'll explain that. And let me just show you what this function is doing. Okay, so this function is basically computing the scalograms for the normal and abnormal signals. Okay, here notice what we've done, right? We are not taking the entire data set. We are taking only 100 samples from each normal and abnormal because we don't want that data set bias, right? Remember in the previous case, we had 5,000 normal and 700 abnormal. In this case, we are limiting both to 100 observations from each. Okay. So that is what it looks like. Let me open up one of these scalograms to show you what they are. So these are saved as JPEG files, and I can open them up as images. Okay, so here, this is what the images look like, right? Zoom is making it very difficult for me to navigate, but okay, yeah, this is what the images look like, the scalograms. Okay, and the resolution is not as good as what we saw in the when we generated the scalograms, but this is what an abnormal signal looks like. So immediately you can see that there are kind of differences between abnormal and normal. The normal signals look very clean. in terms of the frequency, like the spacing, but the abnormal signals, they don't have a proper spacing. And the scaleogram kind of helps us to capture that. Sorry. Okay. Coming back to Sachin's question around how do you read a scaleogram? Let me show you that in detail. Let's see. Okay. There are some slides that I had hidden here, but you can obviously go and look at them. Okay. So remember what I said about a scaleogram. It basically takes these different wavelets and it moves them across the signal and captures some data. Is that part clear? You have a wider scale, a wider wavelet, a smaller wavelet, a very compressed wavelet. These different wavelets, they have different frequencies. Okay. So look at this slide here. For those who are interested in the details of scaleogram, on the x-axis, this is what a scaleogram is. On the x-axis, you have the time. On the y-axis, you have the frequency. So basically, it's saying, in this case, at the lower part of the scaleogram image, I have my low frequencies. At the top part of the scaleogram image, I have my high frequencies. Okay. So when it comes to low frequency, let's say this is my low frequency wavelet. I'm passing it across the signal in two windows. That's it. Because it's spread out. And when I pass it across the signal in two windows, this is what energy bands it will give me. So here, for example, you can see there is a low frequency component. That low frequency component is how slowly this baseline is changing. Okay. Now, as we go higher in frequency, we take shorter wavelengths. The shorter wavelength is going to pass across the signal in more windows, right? It's fitting in the signal in more windows as compared to the low frequency wavelet, right? So here we're getting some little more detail in the scaleogram, right? The high frequencies are very high resolution. So these are being placed across the signal very frequently and they are capturing the high frequency movements. So they are capturing some of this noise, some of these peaks and so on. And those are represented here in the high frequency. Okay. So basically what we're saying is towards the bottom of the scaleogram, you'll have what is the low frequency trend. Towards the top of the scaleogram, you're going to have what is the high frequency trend in my signal. Okay. And if you look at the signal here, the high frequency part is very obvious. It's these spikes. The low frequency part is the small change we're seeing in the baseline. It's a very small change and that is being captured here. Okay. Ujjwal is asking, is it unidimensional? If by unidimensional you mean, is it only going across the signal in one way? Yes. If you want something that grows across a signal in two ways, or rather that goes across an image, then you'd have to use a two-dimensional scaleogram or multi-dimensional scaleogram. So this one is computed using CWT in MATLAB. Okay. Right. So this is CWT function here. If you want to do this across two dimensions, then you'd have to look at something like a CWT2. But when you have a signal, it's always CWT. When you have an image, it will be FFT2 or CWT2 or anything, mod weight 2. That's for two dimensions. So I know a little bit of a detour, but I hope those who are interested in knowing how to read a scaleogram, this is actually what it means. Okay. So remember, we have all of the data now sitting, all of these images we created for 100 normal signals, 100 abnormal signals. The next thing I'm going to do is I am going to split it up again into training and testing. Okay. Now, There's a difference between those features we saw in the previous case and images. Images are huge, and you cannot load all of that into the data in one go because it will crash your computer. So in that case, we use something called an image data store. An image data store is a memory management technique that allows you to load data into memory as and when it's needed. So basically, if I have 1000 images, I'm not loading 1000 images in one shot. I will load it in small batches. Okay. And what that means is I can still do the deep learning because deep learning happens in batches or processing happens in batches. But I'm also making sure that my computer won't crash or my memory will not get clogged. Okay. So that's an image data store. There are signal data stores, text data stores, audio data stores. There are many types of data stores that are available. In this case, since I'm working with images, it's an image data store, basically. Okay. So let's do a quick check what's in my workspace. To find out what's in my workspace, I can type whos and I can see all of these variables are there. Okay. Let me see what is training images. And instead of loading 100 images or 1000 images, it's basically going to be loading, telling me where these images are located, nothing else. Because remember, I don't want to load everything at once. I'm just going to um, uh, load them in batches. Okay, so now it comes to the fun part of actually building the AI model. Did you all see the Deep Network Designer yesterday? Yeah. So if I go to apps, I can click on the Deep Network Designer under the AI apps. And I'll open it here. Okay. So this is the Deep Network Designer. And you can obviously, build your own network from scratch. You can import from PyTorch or TensorFlow, or you can use some of these pre-trained networks. Okay. I am going to use a pre-trained network in this case, which is ResNet 18. Let me search for it here. So if I go, so ResNet 18 is here. I don't have it already, so let me click on install, and you'll probably have to do this yourself. So there's something called the add-on explorer, and this will give me access to the ResNet model. Let me just try to, okay. Okay. So this is the ResNet model. It's got all of the instructions here. Let me install it. This will take me a few seconds. In addition to ResNet, there are multiple other models that you can explore. There's AlexNet, SqueezeNet, GoogleNet, VGG13. Under audio, there are different networks as well, right? Some of the most popular ones. You can build your own network from scratch. I'm just going to bring in ResNet here. I'm not going to open the examples because it'll just save some time. So ResNet is now installed for me. Okay. Let me click on it here in my Deep Network Designer. Oh, sorry. Let me close that and open it again. Okay. Oh, it's importing now, but I think I might have accidentally closed it. Anyway, we'll see. Okay. So this is my network. Have you all saw this yesterday, right? What is the Deep Network Designer? How do you interact with it and so on? I can zoom in and look at the different components here. So for example, remember we talked about convolution. This is my first convolution layer, my second convolution layer, third convolution layer. And that's basically how you build a CNN, convolution neural network. You keep stacking the convolution followed by these other processing layers. Okay. I need to make a couple of changes here. Okay, because I need to adapt this for my application. So let's see, what I want to do is I have in my pre-processing, I took care of the input layers, but now I need to change the output layers here. Can somebody tell me what is the change I need to make? Remember, my application is to predict between normal and abnormal. I have two classes. So here, what is the change that needs to be made? This is my second last layer, and it's able to predict 1000 classes. Will this network work in my case? Anyone? Will this network work for me? It can predict 1000 classes. Right, it won't predict. It won't work for me for two reasons. One is it's not trained on my data, and two is it's got the wrong dimensions. So what I'll do is I'll delete this layer, and I will go and find a fully connected layer for myself here. Okay. Now this fully connected layer, how many outputs should it have? Any answers? How many outputs should my fully connected layer have? I have two classes. Any guesses here? Yeah, two. So I need two outputs, and now there's another point. If you've seen transfer learning, you know that in transfer learning, what we're trying to do is we're trying to leverage this network that somebody already trained, and we want it to work in our application for our application, right? Now, if I retrain, I need to train this network, obviously, but do I need to retrain the entire network? The short answer is no, I don't need to train the entire network. What I can do is pretty much leave all of this top part as it is, because somebody has trained it on huge amounts of data and it's able to generalize. But I only want to train this part of the network, this last part. And from all of these layers, only the fully connected layer is actually trainable because it has weights and biases. Okay. So how do I ensure that I train not the full network, but just this part of the network? Okay. That's where I will leverage weight learn rate factors and learn rate factors basically. Okay. Here I'm putting it as 10 for weights and 10 for biases, and I'll tell you what that means. Okay. Um, okay. So I've made these modifications to my network now. And just for sanity check, let me click on Analyze the Network. So it will do a quick analysis to see if I'm making all my connections properly, right? It says 0 errors, 0 warnings. And this is what my network looks like. I can scroll through the network. I can click on any part and see about its details, okay? After I've done this, I can export the network for use, but I can also do something like generating code. So how do I generate code for such a large network? I'll leave this to generate. Please give me a second. Okay, so my code should have generated by now. If I go into MATLAB, it's very interesting, but you'll see everything from start to finish has been generated for me. So I'm creating a network, I'm adding all of the layers that are needed. And so if you want to learn about how to write this code, you can modify it You can use it as it is. You can make all of the connections, and there you have your code. Okay. You can also choose to export it the um, with the weights and biases if you want. So that's also an option for you. Okay. Instead of doing that, let's export the network directly so that we can use it. And I'm going to just call it net1 for now. Okay, so this part is done. And if you feel like you missed those instructions, don't worry about it, because in the script here, I have written all of the steps you need to follow. Okay, so you can just follow it from here, right? If you want to do all of this using code, right, that's also an option for you. So you can train it. Everything we did with the point and click, you can also do it using code. Okay. So that part about creating a network architecture is done. The next thing we want to do is create some options that will be used for training the network. And remember, in our network, we had actually, for the replaced layer, this convolution layer, we had set the learn rate to 10. What we're doing in our overall training options is setting a very low initial learn rate of 0.0001. That's practically not going to have any effect. But for the convolution, the last fully connected layer, this 0.0001 will multiply by 10 and make it 0.001, which makes it an effective learn rate. And then it will keep working with that. Okay. So remember what we did, that whole learn rate factor, setting a very low learn rate here is actually freezing the top part of our neural network and training only the bottom part of it. Okay. So let me run this line of code. And basically we have all of our training options set here. Okay. You can play around with maximum epochs, which is how many times you want the data to run through your network. What are the batch sizes? Execution environment here is, if you have a GPU, it will select a GPU. Like I have a GPU, so it will run much faster. If you don't have a GPU, it will use your CPU and so on. Verbose means it will print out the progress, but actually what we are going to use is the plots. So that will be convenient for us to see. Okay. And after we've done everything, we've set our options, so we've taken our data, we've taken our network, and we've set our options. We define a loss, and we can run this and let it train. Now, one question you probably have is, what is this loss thing that we've added all of a sudden? So the way we train neural networks is we try to minimize their loss. The loss being the difference between what they are outputting and what the actual true values are. Okay, and here my network is training. So you can see that it's going through the training process, and this is the training loss. Okay, now there are different types of loss that you can use. So if you want to explore that, you can check the train net function which I used in MathWorks, and it will give you all of the information you need about training and so on. Okay, so here I'm in train net. um, I can skip to input arguments, and it tells me, okay, this is the image data you need. If you have sequence data, if you have feature data, what do you do? And this is where the losses are. So depending on what kind of problem you're trying to solve, your loss function will differ. If you're doing regression, you're using one of these. If you're doing a classification problem, you're going to be using cross entropy. So remember, we had categorical labels, normal or abnormal, and so we are using cross entropy. So just go ahead, read some of this. It will give you an understanding of this stuff. Okay, so let me pull that aside. And here it looks like my training has ended. Remember, again, I have a GPU, so that finishes off within a minute or so. It'll take longer for you. And this is what the training looks like. Okay. So it took a little while to converge, but by the 50th iteration, it was able to converge. So that plot will also come and sit here in your live script after the training has happened. Okay. Yeah, so recommend using a GPU, but if you don't have that, you can still run it on your CPU. It will just take a little extra time. Okay. So now what we want to do is test the performance of the network, right? And we've called this, the train network is called ECGNet. So basically, I am going to now test the performance of this network. And what I'm going to do is look at the predicted labels from the network versus the true labels of the network, and I will compute the accuracy. In the last case, we used N and Z and then divided by the total number. You can do that as well. You can also use mean. And here we can see what our accuracy is. In addition to accuracy, we can look at confusion chart. And this is what my confusion matrix is showing me here. So all in all, it looks like deep learning worked better than machine learning, which is expected in some cases. But obviously, deep learning requires more, if you have a GPU, it's better, requires more playing around with the data and the architecture as well. Okay. So just to recap here, what we did was we took our signal, we computed its scalograms, we trained a neural network on the scalograms as images, and then we're using it for inferences. Okay. So this is what the general AI workflow would look like. And you saw that in our case, we did mostly part 1 and part 2. If you're interested in learning about this part 3 and part 4, let us know. We can point you towards some resources or discuss those with you as well. When it comes to just a little bit of added information, when it comes to the whole time frequency domain, how do you pick the right transformation here, right? Do I use a spectrogram, which is based on FFT? Do I use a scalogram, which is based on CWT or, wavelets? Do I do some of these other things, different types of transforms? It really depends on what is your application. So if you have an application like ECG where your signal is moving very rapidly, then you might want to use a wavelet spectrogram because it can capture these high frequency motions. If you have a signal that is moving very slowly or not too fast, then you may want to use a spectrogram because a spectrogram is easier to compute. If you're doing something with speech processing, then a good option would be a MEL or a Bach spectrogram because these are optimized for speech processing applications, right? And so on and so forth, right? If you're interested in knowing a little more about that, you can visit the time frequency gallery here. And this tells you what is the computation, time frequency computation. And it also shows you examples around using these, right? So you can go and try out these examples. So for example, rock music, you can go and try that out. And this is the example, right? All you have to do is click on copy command, and then you come to MATLAB. Sorry, where is MATLAB? And you just paste it here in your command window. And it will open up the example for you, all of the files that you need, everything. It will take you to a folder where you have everything you need and you can just run the example as it is, right? So whenever I say go try out an example in MATLAB, it's very simple for you to go ahead and do something like this, okay? So for those of you who want to explore the signal processing, time frequency stuff a little more, that's something you can try out. Summary of what we looked at today: the wavelet part, scattering, machine learning, deep learning. And if you want to go a little more in depth with any of these topics, let's say AI with signal processing, time frequency analysis, wavelets, or even the ECG problem itself, go follow some of these links, right? It will be useful for you. And before I open it up for questions, I don't know if you've heard of something called the MATLAB Academy. So there's a MATLAB Academy where you can take these online self-paced learning. Okay. So depending on whether or not you have the MATLAB license through a university, you will get access to different kinds of things. If anything says on-ramp, it's free. You can go and take these courses right away. There's machine learning, there is image processing, computer vision. I'm sure you've seen some of these already. But if there's something you want to do in detail and you have the campus-wide license, then you can go to more advanced things like, let's say, you can do just 1 second. Let me see. Sorry, I've just got all of these filters here. I can't. Oh, yeah. So let me go into course, and then you can do some of these slightly longer, like 8 hours of Simulink fundamentals. Or if you want to explore only the plotting and data visualization, there's a 90-minute course on that, and so on. Okay. Specifically for signals with AI, there are something called learning paths, which you can explore. So let me clear this and let me go to learning path. And here it shows me like, machine learning techniques, deep learning techniques for images, core signal processing techniques, and so on. Okay. So go and explore these. A lot of them are available for free. You will get a certificate. You can put that on LinkedIn. You can put that, on your resume or something like that. Please feel free to explore that. If you have any questions, do reach out. Like I said, I'll share this slide deck. It's got all of this additional information that you will have access to. So I'll upload a PDF version of this. If you have questions, do reach out and try these exercises I've put in the folder. They'll give you a nice understanding of the hands-on application of AI. If you have questions now, if you want me to show you anything, we have 15 minutes. So please feel free, use the chat or use the, just unmute and ask. That's also fine.
Yes, dear participants, you can ask the question in the chat box, or else you can unmute yourself.
Yeah.
Ma'am, I would like to tell you that we have shared the links regarding the on-ramp as well to the participants.
Okay, thank you,
We
ma'am.
had asked them to complete them the courses related to image processing on-ramp, AI, and machine learning as well.
Oh, that's great. Yeah. Thank you, ma'am. Yeah.
Hello, ma'am. Excuse me.
Yes, ma'am.
If
Go
I
ahead.
want to process real-time signals like
Yeah.
EEG signals, I worked on those type of signals in my research.
Yeah.
But I got some problems when I came to know about when I came across processing of real-time EEG signals. So
Okay.
so, what kind of techniques or to gather those or eliminate the
Yeah.
eliminate its noise? It I found it so troublesome in that
I
case.
understand. So where are your signals coming from? What is the source?
Signals, brain signals, EEG.
EEG signals. Okay.
Yeah.
Okay, this is for participants. Sorry. So the thing is that when you're working with real-time signals, you probably need to do a little extra data management. So for example, you'll have to work with buffering the signals and applying some processing to small buffers of the signals. You can't do it sample by sample, right? Obviously, that's not possible. So you'll have to look at buffering techniques. Just Google it, look at real-time signal processing in MATLAB. Are you looking at deploying any of your algorithms to any hardware or something like that?
No, not that case. It
Okay,
was a classification problem.
okay,
Yeah. So deployment, I am thinking about that, but I could not do that. Uh, I could not reach up to deployment
okay,
on any
okay.
particular cloud platform.
Right, right. So my advice to you would actually be whenever it comes to real-time stuff, right?
Yeah.
Um, real-time systems, I think Simulink is the best because Simulink is designed for dynamic real-time signal and system design. So in
Oh,
that case, you might want to just look up um, uh, real-time signal processing with Simulink, but
okay.
you can also give a try to this link I'm sharing here. This is how do you process streaming signals in this is in the MATLAB Academy.
Okay. Okay.
Okay, so this will give you a slight idea of how to get started, and if this solves your problem, that's great. Otherwise, I would suggest that just explore a little bit in your on the MathWorks website. But I think this
Oh,
might be a good start for you. The whole how do you deal with streaming signals, buffering, signal processing, and batches, and so on.
okay.
Yeah,
Okay.
sure.
Thank you, ma'am. Thank
Yeah,
you.
sure, ma'am. Yeah, thank you. Um, any other questions? I'm here for another 10 minutes. Can also drop me an email. My email is, I'm putting it here. Yeah, I've shared my email here. So reach out to me here on LinkedIn. I mean, anywhere is fine. Also, feel free to reach out to my colleagues, Nikhil, Kunal, or Ankit also. Like all of us work in a group, so we're here to support you.
Yes, participants, you can unmute yourself and do ask the questions if you have any queries, or else put it in the chat box.
Maybe before I leave, can we just, how many of you are working in medical imaging applications? How many in medical signal processing applications? Anyone wants to share? Because I'll just put in some resources here for you. Okay, so let me put in some resources here. Um, for those who are working in medical imaging and you want to really look at some cutting edge stuff, have a look at this video. It talks about different AI techniques also for medical imaging. Um, medical signal processing. Let me share something. I couldn't get into details because it's a very short session, but um, I'll share something that yeah. So this is for this one you can check out for signal processing applications. So this video I shared covers a little bit of what I presented, but then also stuff like pre-process, I mean, including with Simulink, system level integration, generating code for deployment, that is also covered here. So you can check that out as well. Yeah. And whenever you have questions related to signal processing, AI, anything like that, just feel free to Google stuff and use the MathWorks tag, and you'll find either videos, GitHub repository, um, um, documents that can, examples that can help you with some of these topics you're interested in. Yeah. Okay, then thank you everyone. You've been a very patient audience. Thanks a lot. And do try out the examples that I shared. Feel free to reach out to us at any point, and have a great day. Bye-bye.
Thank you, Nikita ma'am, for sharing your valuable time and insights with us. Your session was truly enlightening, but also inspiring to many of us, those who want to work in future in the biomedical field. You have bridged the gap between the theory and real world applications with clarity and depth, shedding the light on how AI is revolutionizing in healthcare diagnostic, medical imaging, and signal interpretation. I would also like to say that your expertise was a unique vantage point at the forefront of AI in academic and industry. It has brought immense value to our understanding. Thank you so much for joining us and accepting our invitation. We would be happy to be connected with you in the near future as well. Thank you. Thank you so much. Thank you to all the participants for participating in this 5 days, 1 week national level FDP. I appreciate your presence. It was truly meaningful. Thank you for the enthusiasm you have shown and the thoughtful questions you have asked throughout the FDP. With this, we conclude our FDP we have concluded with the FDP. Thanks to all. We will be sharing a test link by today, 5 p.m. in the evening. Make sure you attend the test. Yes, you can leave now. We conclude that the FDP is over. Thank you all. Thank you.